So we've seen a simulation of sampling distribution now. So we're ready to talk about the central limit theorem. The central limit theorem itself states that for a population with mean mu and standard deviation sigma, the distribution of sample means is approximately normally distributed. And the mean and standard deviation of that sampling distribution are given by mu sub x bar, that is the mean of the sampling distribution, which as we saw was actually equal to the mean of the population itself. The standard deviation of the sampling distribution, a little bit less obvious, is actually equal to the standard deviation of the population over the square root of the sample size. Now, if the population itself is known to be normally distributed, then this will hold for any size sample, no matter how big or small. That being said, in looking through the simulation, we also saw that when we used a random distribution or a uniform distribution, that we needed a very, very, very large number of samples, hundreds of thousands, if not millions, before we saw the normal shape really emerge. So that higher threshold means that that longer time to kind of converge on a normal distribution means that we're going to need a kind of a minimum sample size requirement. So for populations that are not normally distributed, or simply we don't know the distribution, a minimum sample size of 30 is required. So this is the required sample size for any population. Now, as it turns out, because of the nature of the problems that we will see in this section, most of the time we are going to assume the population is normally distributed. And again, the theorem still produces a bell-shaped curve. In more advanced levels of statistics, you'll learn that that curve, if it's flatter and wider than a normal distribution is supposed to be, then it actually has a slightly different name, despite looking very, very similar. And you'd also talk about why the 30 becomes important, but the minimum sample size is typically 30, unless we happen to know the population is normally distributed, or we're assuming that, in which case we can get away with a smaller sample size. So let's take a look at an example here. So we have the heights of fully grown white oak trees are normally distributed with a mean of 90 feet and a standard deviation of 3.5 feet. So we are told that they are normally distributed. That means that we get to work with this assumption. Random samples of 15 trees each are selected from the population. So much like what we saw on the simulation, 15 trees are randomly selected, and the mean of that sample is calculated. And then another 15 are selected, and the mean is calculated. And then another 15 would be selected, and so on. And if we did this enough times, we would start to see a normal distribution emerge. And the sample size is only 15, but because we are told that the heights of the trees are normally distributed, since we have a normally distributed population, we can get away with a smaller sample size like 15. So, to start with here, we're going to determine the mean and standard deviation of the sampling distribution. That is to say, we need mu sub x bar, but mu sub x bar is the same value as mu, which in this case is 90. Sigma sub x bar is equal to sigma over the square root of the sample size. So 3.5 over the square root of 15. Now, regardless of whether the sample size is a friendly number for a square root, the division and everything means we're probably going to end up with something less than nice here. So the usual rounding rules will apply. The standard deviation of the population is at 1 decimal place, so we'll do that here as well. So this actually comes out to be 0.9036, etc. We can round that to 0.9. So we've got our mean of 90 and our standard deviation of 0.9. Now, I have two normal distribution curves down here, and the idea is that I'm going to label them with the mean and standard deviation of each one. So this first one is going to be the distribution of our random variable x, which is the height of the oak trees, and it is, it is normally distributed with a mean of 90 and a standard deviation of 3.5. That's going to put 90 in the dead center, and then for each tick mark we go away from 90, we're going to add 3.5. So here we're at 93.5, then 97, then 100.5. On the other side, 86.5, 83, 79.5. Now, the sampling distribution, this time our variable is not x, it's x bar. It is the mean of a sample, not an individual data value. These are normally distributed with a mean of 90 and a standard deviation of 0.9. So again, 90 in the center, but adding 0.9 to that every time we go out 1 tick mark. Or subtracting. So, I mean, these two pictures look the same because the size, the dimensions of the picture are the same. But if we look carefully at the scales of them, what we can see is that 92.7, 3 standard deviations out to the right, and 87.3, 3 standard deviations out to the left on our sampling distribution, well, those values actually would fall roughly around here. Our entire normal distribution for the sampling distribution is contained in just this little section here. So it's a much narrower distribution. Again, I have the picture scaled the same, or size the same, but the scale on the axes tells us that the sampling distribution is much narrower than the original distribution. Now, how does this figure into probabilities? Let's ask ourselves a couple of questions here. First, let's find the probability that a single randomly selected white oak tree is taller than 92 feet. what's the probability that the value of our random variable x is bigger than 92? Well, again, we're looking at x having a distribution that is normal with a mean of 90 and a standard deviation of 3.5. Now, I could label all of it, but what I would like to do is focus on where the 92 is. If 90 is in the center and 93.5 is is the one standard deviation to the right, then 92 is going to be approximately here. And that means that we're looking at an area of this region. Now that's not, that's not a tiny region. It's less than half of the area under the curve, certainly, but it's not teeny tiny. It's not unusual, highly unusual to have that. I mean, 92 isn't even one standard deviation away from the mean. So again, this is not particularly unusual to have a value such as this. And the probability of this, which we can obtain from the, using technology. I'll use the command for the TI-84 calculator. Normal CDF from 92 to our version of infinity, whatever that may be. A large enough number like 1 million is quite sufficient. A mean of 90 and a standard deviation of 3.5 gives us a probability of 0.2838, etc. So, again, not incredibly unusual. A 28% chance that a randomly selected tree is going to be taller than 92 feet. Okay, so nothing new there. The contrast here is now in the second question. Determine the probability that a sample of 15 randomly selected white oak trees altogether has a mean height greater than 92 feet. Now remember, the sampling distribution, while it is normal, and while it does have the same mean, it has a much smaller standard deviation, 0.9. So simply going out one standard deviation isn't enough anymore. We're going to need to go a little bit further. To find 92 here, we're significantly further to the right. And the region that we're looking for the area of is significantly smaller. So we're going to get a very different probability from this. This time, we're being asked what's the probability that the mean of our sample would be greater than 92 feet. And again, we'll use the calculator for this. Remember, though, that we have a different standard deviation from before. And we get a considerably smaller probability. Which goes, of course, with the considerably smaller area. Why the difference? I mean, obviously we can see from the different standard deviation that we are definitely going to be further out to the right and therefore have a smaller size region that we're finding the area of. But why? Well, the clue here is in the differences between these. In the first one, we're picking a single tree. A single tree having a standard deviation, having a height of 92 feet is not terribly unusual. Certainly, it's not hugely common either. It's 28%. So not out of the realm of possibility, certainly, but most of them are not going to be that tall. Now we're taking a sample of 15. Now, in that sample of 15, some of them might be smaller than 92 and some of them might be bigger than 92. But in order to have a mean of 92, there has to be enough trees that are bigger than 92 feet to balance out any that are smaller than it. And the fact of the matter is that there is a much bigger chance of having a tree smaller than 92 feet than there is of having a tree greater than 92 feet. So now we're saying out of 15 randomly selected trees, we need to somehow get more of them, or at least as many above 92 feet as below. But if there's a 28% chance of getting them from that, of getting a tree that's above 92 feet, that means, by the complement rule, there is a 0.7162, almost 72% chance of selecting a tree that's smaller than 92 feet. So now we're trying to say, all right, we've got basically almost 3 times the chance of pulling a small tree as we do a big tree, and yet we're somehow supposed to come out with basically an even number on each side so that our average comes out to be 92. That's pretty unlikely. You know, I mean, playing the odds here, if we pull a sample of 15 randomly selected trees, I would think that about 70% of them, you know, think expected value, I would think about 70% of those 15, or maybe around 10, 11 of those trees, are probably shorter than 92 feet. Whereas the other 4 or 5 then would be bigger. And the thing is that those 4 or 5 that are bigger are not going to be enough to balance out the 10 or 11 that are shorter. To land at 92 for the mean, you kind of have to have it pretty even. You know, you'd have to have maybe 7 or 8 above the mean and the others below. So, that seems like it would be pretty unusual to have a group of 15 where you get, you know, 7 or 8 that are higher than 92 feet. So that is the big difference between these. And a lot of these problems, and as I said before, a lot of these problems are going to start with the assumption that the population distribution is normal, so that we can make this kind of comparison between them. And then we can see the difference. The big key to them is whether you're picking a single randomly selected item or whether you're picking a sample of several randomly selected items. So that's what you have to pay attention to here. If we're being asked about the probability of a single randomly selected member of the population, we do a basic normal distribution, nothing fancy. But if we're being asked about the probability of a sample having a mean, that's when we're going to turn to the central limit theorem and use the formulas mu sub x bar equals mu and sigma sub x bar equals sigma over the square root of n.